Hello and welcome to Introduction to Machine Learning for Beginners, Part 2. In the previous video, we saw some of the applications of machine learning, and we also saw why in this particular time, machine learning is getting more and more attention. And we discussed certain factors, for example, availability of data and computing power, as well as the software stack. Then we discussed the learning problem using data, and we discussed some types of learning, for example, supervised learning, unsupervised learning, and one other kind of learning called reinforcement learning. We discussed that. And then we moved towards different, for example, data formats. And we discussed images, videos, audio, text, and some encoding methods, particularly for text data, which is called the one-hot encoding. And then we discussed the data standardization. So after that, we moved to model, which is the core of machine learning. What a model is, we discussed that it's basically a function in feature space, and we discussed certain terms, for example, dimensions, parameters, and hyperparameters. And then we move towards the cost or error. What do we mean by cost or error, and what do we mean by optimization? And we actually end the last video while we are discussing overfitting. So I will, in this particular video, I will start again from overfitting. So, and then we will move towards generalization and data snooping and the link of all these concepts with probability distributions. And after discussing that, I will just get a digression, and I will discuss some of the recent advancements in machine learning, sometimes known as deep learning. So I will discuss very briefly what deep learning is, and after discussing deep learning, we will be moving towards the understanding of the general pipeline of any machine learning project. And after discussing that, we will actually do one face recognition application today in Python. So that's the agenda of today's video. So let's start. As I discussed in the last video, that overfitting is really a bad thing. To describe overfitting again, it is a consequence of choosing a very flexible model, and the consequence is really bad. The reason is, if you, for example, fit your training data very, very well, then you lose the chances of the generalization. Generalization means how the model performs on unseen data. For example, it is possible, and it actually happens normally in real data, that a lot of data points, if not all, a lot of them has noise. And when you choose a very flexible model, a model that can adapt, that is flexible to go wherever it wants. If you choose a very flexible model as your function for fitting, whether you are working in regression or classification or whatever other learning paradigm you're going with, if you choose a flexible model, then the model will not only get the pattern, the model will not actually try to get the essence of the pattern. It will try to fit each and every data point exactly, and with that it will fit the random noise as well, thereby going away from the actual pattern of the data. And what will happen due to noise, the parameters of the model, they can become in such a way that it missed out actually the pattern of the data, and on unseen data it performs very poorly. Let me give you an example. For example, let's say your actual data lies on a line with some noise, and maybe there are some outliers, maybe some data points that are just due to noise. I mean, they have a lot of noise. If you, for example, fit a very flexible model, maybe the model goes like this, um, like, like this, and that model may go like so. However, a better model, and this particular model, tend to perform very poorly on the data, on the unseen data. For example, let's say these are more points on the data. Let's say these are many more points on the data. Let's say that were unseen. So you can see that the model at this particular point is trying to say that the actual prediction is this one. However, the actual prediction should be here at this. So yes. So as you get your model more flexible, it tries to fit each and every training data point very well, thereby actually decreasing whatever your error cost on the training data, and that actually brings a problem that it may not perform very well on the data that is unseen to it, because it does not get actually the pattern, it actually memorizes the training data, which is a bad thing for generalization, which is not desirable. And one way to avoid overfitting, as discussed in the last video, is to actually restrict the parameters of the model to gain little values. By little value, I mean, for example, if you have a particular model with parameters A, B, and C, then somehow restrict that the value of A should be small, restrict that the value of B or magnitude of B should be small, and the magnitude of C should be small. So restricting the magnitudes of different parameters to be small values actually restricts the flexibility of the function, or applies the regularization. So this way, the flexible function is not that flexible. I mean, it does not go the way it wants to go with the parameters with high values. For example, if you have parameters with very large magnitudes, then the function may behave in a very flexible manner, thereby going towards overfitting. This regularization is one technique, and it has some theoretical backgrounds as well. I mean, this is not just a hit and trial thing that go and just decrease the magnitude of the parameters. There are probabilistic relationships why this actually happens. And this regularization is so much famous. I mean, people tend to come up with a model, maybe a flexible model, just to be very greedy in a way that the flexible model will learn the pattern very well. But then due to the fear that it may overfit, they actually decrease the flexibility of the model gradually by applying more and more regularization. And now, even having a flexible model, you are now going to play with the regularization parameter, which means how much regularization should I enforce. And to get a good value of regularization parameters, there are ways to do that. Basically, the cross validation does that, and so on. Rather than going from a simple model to the next higher level of a relatively less simple model to the next progressively, that might be one way. The other way is to go and pick a flexible model, but then be careful. Don't allow the parameters to be so huge. Or maybe if you want to allow the parameters to be so huge, decide how much. And that's precisely what we mean by regularization. And that's how the regularized version of the model, it actually performs very well on the unseen data. You might be thinking, what do we mean by unseen data? Once we are given the training data, a lot of it, we have that data, and once we have that data, we actually fit a model on that data. Now, how can we evaluate the generalization of the model? So the question really is, given we don't know, when we can only know the data that is unseen to us when we actually deploy the model. And when we deploy the model in some real scenario, at the point where it should be deployed or stuff like so, only then we will be having the unseen data available to us without any labels. There, the model actually will be performing or actually labeling the unseen examples. The question is, um, before actually deploying the model somewhere in real environment, how can we validate the model? How can we evaluate the model? How can we get the expectations, a look and feel, a belief that it will perform what on unseen data? And that brings a question: what is unseen data? I mean, the data that is given to us completely, all the data is training data. What is unseen data? So what people do is, for example, if you're given a lot amount of data, let's say training data to train your model, let's say that's your model, that's your data. What people do is people actually keeps a fraction of the data out, let's say 20%, or maybe this percentage is debatable. Some percentage of the data, they actually extract that data or remove that data from the actual set and work only on the rest of the data, let's say in this case 80% of the data. So what they do really is they train all their model, they set all their parameters on this 80% of the data, which is called the training data. And then once the model is, once the confidence about the model becomes really high, that the model is performing very well and stuff like so, then actually the model is evaluated on the data that was removed earlier. Because now this data, this 20% data is unseen to the model. And we can evaluate our performance of the model on this data. And we can see how the model generalizes on unseen data, because now we have created an unseen data. The problem with this split kind of things is the training data normally is always small. You always need more and more examples, to more and more data to actually train a model very well. So it may look a bad idea to actually cut off the training data and even reduce it and then train a model, because we are not utilizing a significant amount of data in the process of training. Maybe this particular data that we just cut out, if we use that data as well, the training becomes more valuable. But then the question is, how will you validate? The second fix might be to reduce the percentage of this set, sometimes called the validation set. Reduce the percentage of the validation set. But then if you reduce the percentage of validation set to very low, then the expectations of generalization in unseen environment becomes questionable. And the reason is, all your expectation will be on a very small set, and that may not be a good idea to get an expectation. To get an expected value, you need your validation set, or the set you are going to perform on should be larger in size. So to get a good expected value for the generalization, you need the validation set to be larger, but then you will be having small training set, which is a bad idea for training. So this split size is really debatable, and it really depends. So there are heuristics, there are rules of thumb people or practitioners came up with to get these splits and to just work very well. For example, depending upon the amount or quantity of the data, the splits may vary on data to data. But this generalization actually is achieved by, or the expectation, the belief that how will it perform on unseen data is achieved by first creating a validation set, then evaluating the model on whatever the trained model is on the validation set. If the evaluation is poor, you may go and change the model, either by selecting a different model class or maybe by applying a different amount of regularization and stuff like so. So that's what validation is. One more thing that is related to it is something that you should notice is data snooping and the test set. Remember, in the previous case, the validation set, it actually plays a part in the training process. Because once you train a model, then you evaluate the model on the validation set. Then you have a look and feel that whatever model you was using or you have just came up with, what's the performance of that model, and that validation set and evaluation of on the validation set gives you a clue whether you should go and change your training and all that process or not. So one way or the other, this validation set is actually helping you in the training process. Whether you go change your model, train the model differently, go and set the regularization parameters in a different way and stuff like so. So validation set is playing a lot role in the training. Well, the test set is something that is, so the actual split is like so. That's your training set. Let me describe this as TR. This is, let's say, your validation set. And from the original data, you may split some data which is called the test data or the test set. What you do is, test set is the completely unseen data. Or you can define test set as a set of data that never plays a role in training, that never guided the training process. That is what the training test set is. Validation set, however, guides the training process. So what you can do is, you actually should have three splits on the data: the training data, the validation data that actually is used to improve the training again and again, and so it actually helps the training process or is involved in the training process. But the test set should be kept completely untouched until you finalize the model after all kind of evaluations on the validation set and so on. And then the evaluation on this test set basically is your generalization. That's a measure of generalization, how it works. But what happens normally is the following. What people can do or is the following. For example, you may have a training set, you may have a validation set, you do a lot of processing on this, you select a model, and that's a tricky part. Get a model right, get all the parameters right, you do a lot of stuff. And then you evaluate the model on the test set, and you just get, no, the performance is not the one that I was really expecting. On validation set, the performance was really good, but just on the test set, it decreases. So let me go back and just, for example, change a few parameters a bit and then go back to test set. Well, if after evaluating on the test set, if you go and you change your training parameters or process, then this test set is no longer unseen data. It is guiding the training process, and evaluation on the test set may not be a good measure of generalization on the unseen data. And that is precisely what is called the data snooping. Another example of data snooping might be that, for example, somebody just published a paper and published a data set. For example, there is an algorithm that is the best algorithm, for example, for a particular task. And that's the data set. On this particular data set, the algorithm performs very well. And several times what happens is the people who actually generate these benchmarks, the data sets, they actually provides the splits. So that's the training data and that's the test data. For example, they supply the split. And what people do, people pick the training data, split the training data into train and validation part and do a lot of stuff, and then eventually test on the test data. But what happens normally is a lot of people use the same train and test splits. And for example, algorithm 1 says that on this particular data, the result is this much. Algorithm 2 says on this particular split, the test results or the generalization results are this much. Now you are seeing all these algorithms and their results. And now after seeing all the results on this particular test data, you are deciding your new algorithm, let's say A3, and you are thinking that A1 on the test data has this particular performance, which means these kind of parameters may be assumed to improve the test accuracy. And algorithm 2 has this kind of measure on the test data, which means if I just increase these kind of parameters or improve these kind of parameters or may come up with a new strategy, then I can do very well on this test data. Now you come up with your algorithm and you report the test accuracy on this test data. Now my question is this data split test is really unseen for you? No, because you are seeing the work of previous people and they have reported test accuracy on this particular test data, and you are using that information for your training process, which means this test data is no longer unseen for you or no longer test data. And this is precisely what do we mean by data snooping. So try your best to not caught by this data snooping. This is really sensitive and very tricky to just analyze what do we mean by test. Remember, test set is a set upon which you measure your generalization, and that set by any means should not be involved in the training process. That's it. So yeah, it's important to focus on this data snooping. That's a tricky thing to have. Next we discuss, for example, the relationship of all these features and data with probability distributions. I'm going over these topics. These are, very involved topics. I could explain these topics in length, but here in this short video, I'm just going over through these topics, different concepts, a little quickly and briefly. However, we have a full-fledged course that actually discusses all these concepts that you have seen so far, and you will be seeing in this video from now on. We have discussed all these in a full-fledged course of Introduction to Machine Learning in a bit more length, in details, and even with the parallel coding in Python. And we tried to explain each and everything with examples, with the live coding examples. So to get a better look and feel, I would suggest to look into that course as well, because it has a lot of explanations. Okay, the curse of dimensionality. Let me discuss that. Any, for example, supervised learning algorithm, whether it's a regression model or a classification model, it eventually computes, at the very end of the day, it computes the probability, let's say, of y being in class C, given that the feature vector, let's say this is t, maybe, given that the feature vector takes a particular form, let's say a list of numbers and stuff like so. These are called the features. So one way or the other, every regression model or classification model, it actually is going to estimate this probability. What is the probability that my target is C when I was available with this particular example or the feature vector data? And you may compute these probabilities for all different possible labels or targets, and then you may pick the maximum to decide what the label is based on the maximum probability. So this is there. You have to, whatever classifier you are working in, whatever regression model you are working in, you actually are estimating this probability distribution. Sometimes you are estimating this probability distribution directly, and in that case we say that's a discriminative learning or discriminative model. And sometimes you are basically learning this probability function using a particular formula called the Bayes formula. In that case, we say that you're doing generative modeling or generative learning. So what Bayes' theorem says is that probability of A is an event, probability of A given B is simply probability of B given A into probability of A divided by probability of B. That's what the Bayes' theorem says. But then to estimate this probability, we can estimate this probability function directly. That mostly is done in discriminative learning, or we can estimate this using the estimates of its components individually. Each component itself is a probability distribution. And to come up with a probability distribution from the data, for example, if data has just one feature, we may bin out the data and see, okay, in this particular bin, how many data points fall? In this particular bin, how many data points fall? In this particular bin, how many data points fall, and so on. And depending upon the fraction in each bin, fraction of data points in each bin, we can decide the probability for different intervals. Okay, but if the data becomes two-dimensional, for example, it has two features, feature 1 and feature 2. Now we have to define these bins like squares. How many data points fall in this particular square, where x varies from this to that and y varies from this to that, becomes one square. How many data points are in this square? How many? And based on the fractions of the data points falling in each kind of bin here, which is a square, two-dimensional bin, we can assign probabilities to each bin, which is defined by an interval in x and an interval in y. But you see, by increasing a dimension, the number of bins, they just increase. And to estimate the fraction, which is a probability measure in each bin, we need a lot of data points in that fraction to get a stable measure of probability. Yes, which means if I increase a dimension, the demand of data will increase to reliably compute the probability measures through binning. Although there are other methods, but the underlying bottleneck is the same. You have more dimensions, you need much more amount of data. Think, for example, you have 3 dimensions. You have 3 features: feature X, feature Y, feature Z. Now now in that 3-dimensional space, you are defining a lot of cubes, and then you actually think how many data points in each cube are there, thereby defining or approximating the probability based on the fraction of the data that lie in that cube. Now you can see in 3 dimensions, the number of cubes, they become large. I mean, so many of them. And to estimate the probability for each cube, we need a reasonable fraction of the data points, at least to guarantee that will fall. To estimate the probability measure reliably, we need a lot of data points to fill these. We are not requiring that each and every bin should be filled up very reasonably and stuff like so, but we need a lot of data to actually get a look and feel of the distribution of the data in different bins. If you have a lot of bins, very small amount of data, for example, a lot of bins will stay empty. Does that mean that probability for those kind of spaces is 0? No. If you could have a lot of data, then we may have some points or maybe several points on those. I mean, having more and more data will give you a reliable measure, and the demand of data becomes significantly the demand of data increases significantly with the dimensions, and that is what we call as curse of dimensionality. And there are ways to deal with curse of dimensionality. If your original data has a lot of features, there are ways to reduce the features, reduce the dimensions of the data, which means reduce the features of the data, and keeping in mind that we are not going to lose the information. Sometimes we do this dimensionality reduction using a method, using a view in mind that whenever we want to reconstruct our original data, we could, and that resembles to compression. And one very famous way of doing that is PCA, principal component analysis. One way of doing that. Although and other ways of using this, other way of doing dimensionality reduction is discriminative, where we do not need actually to decompress our data. We need not to reconstruct the original data back, but we want our original features to transform into the new features, which is a small set of features, but then the classification or regression model, it performs very well. The data after the dimensionality reduction become more varied among different classes. And there are several ways of doing that, but one famous way is Fisher's linear discriminant, or linear or discriminative modeling, for example, we can say. But I've just given you this is discriminative modeling, in which there is no guarantee that you will be reconstructing your original data back. And here the original data will be back. But either way, there are so many methods of doing this dimensionality reduction. We have a full-fledged course on dimensionality reduction where we discuss each and every method in a huge detail. Yeah, so increasing dimensionality is also sometimes important. I mean, you might be thinking that's completely the other way around, but in sometimes it is useful to actually add more features, to generate more features from the existing features, increase the dimensionality of the data, push all the data to higher dimensional feature space to actually get a discrimination. So that is also important. So whereas more dimension is bad in some cases, in some problems, I mean, increasing the dimension becomes necessary. So that's also there. Yeah. So next, what we discuss next is basically deep learning. So just an overview of it, just an overview of deep learning. Although we have a course on deep learning, a separate course, but here I just want to explain the very basic concepts of deep learning. It is basically these are also the models, like the models you have seen earlier. These are also mathematical models that can be used for both regression, classification, and even for segmentation or clustering. They can be used for reinforcement learning and stuff like so. A lot of things are happening in deep learning. Deep learning models are popular these days due to several reasons. One reason is that they have a lot of representation power. They can model any boundary, any real boundary. They can model that with certain assumptions, but they can model that. Further, they have much more data utilization capacity. What do we mean by that is if you have much more data available to train your model, deep learning algorithms, or basically the neural networks, sometimes called the deep neural networks, they can utilize the huge amount of data very well for training, as compared to the classical algorithms in which the data utilization capacity is not that high. What that means is up to a certain level of input data, training data, the model will perform very well, or will adapt to the learning of the patterns very, very well. But as the amount of the data get increasing more and more, the classical algorithms, they do not utilize the data with that efficiency as compared to deep learning. So this is one, and further they have a lot of representation power. And the third, the training and the expansion of the model, making a model more flexible, less flexible, all these kind of things are very much in an incremental and layered way. Very good to control, very easy to control, very efficient to implement and stuff like so. So what basically happens in the deep neural networks or deep learning is, let's say you have a neural network. What a neural network is basically, consider, for example, you have a lot of features, let's say x1, x2, x3, ... let's say xd. Let's say you have a lot of features. You have, let's say, d-dimensional feature space. You have a lot of features. By a lot of features, I mean, this is one data sample and you have a lot of features of it. What you do is you weight your first feature with W1. That W1 is a real number. W2 is a real number. Similarly, you weight your final with WD and you add them up. So basically you do the weighted sum, and this is denoted by the weighted sum. So what this does is basically x1 w1 plus x2 w2 plus x3 w3 plus so on xd wd. Yeah. So then what you do is whatever that number, that eventually will become a number for one example. And whatever that number is, you apply some activation function on it. What activation function is, maybe the activation function is just a threshold. For example, if that particular number, that is the weighted sum of the inputs, if that is larger than a particular number, for example, then then proceed by producing 1, otherwise proceed by producing 0, for example. Or this activation function may be a different one. So that whole one kind of unit is called one neuron, also sometimes called one perceptron. And perceptron and neuron, these terms are normally used interchangeably these days. But what one unit of processing in deep learning is, it accepts a lot of inputs and weight them, and the weighted sum is passed through an activation function. That activation function actually produces some result that may not be just a binary result, that may be a continuous result, any result, but that activation function must be there. That is one unit. For example, that's a processing unit, that's a processing unit, that's a processing unit, that's a processing unit. In the layered architecture, what happens is you may have, for example, an output coming from this unit and an output coming from that unit, an output. One unit is seeing all the inputs to the previous layer. For example, this input is all the outputs of the previous layer. They now become inputs for this layer. And again, you can have that's completely a separate unit. You can have activations on that and they will produce certain results. And you can have one more layer here. For example, in this first layer, we have 4 neurons. In this second layer, we have 4 neurons. These layers are called hidden. I mean, all the processing layers except the first layer that actually has input features and the last layer that actually see the output labels. Other than those layers, all the layers are called hidden. And the hidden layers, they can have arbitrary kind of structure. What particular structure, how many layers should be there in each layer, how many neurons should be there, what kind of activations function should I use, how many layers should I expand, how flexible it will become, and stuff like so. All these are hyperparameters. I mean, these are parameters that you design rather than you learn. And different designs are suggested. I mean, a lot of practitioners came up with a lot of suggestions. And one good way is to just start with those kind of models that are already performing well, and may then tune the model by changing, or maybe changing the parameters, hyperparameters or parameters, according to the available data. And these, this neural network, the term deep appears when you have hidden layers. For example, if you have one or more hidden layers, then you are deep. The neural network is called deep. If, for example, you have several hidden layers, we will say, okay, the neural network is much more deep. And today it is common to have, for example, hundreds of layers of neurons. And the total number of units are just in, thousands, and the total number of parameters are maybe in millions or even billions. It is common. But keep in mind that adding more and more processing units and layers will make the total number of learnable parameters high, and that will make the overall model flexible, and you may get into the overfitting problem that we discussed earlier. And in deep learning, in this deep neural networks, there are different kind of ways, the sophisticated ways, very specialized ways to avoid overfitting in deep learning. One famous way is called dropout, but there are others as well. So And this kind of neural network architecture, this is general for any kind of problem, but there are specialized kind of architectures as well. For example, another architecture called another deep learning model called convolutional neural network is convnets. Convolutional. I don't know I'm spelling this right or not. Convolutional neural networks. They are best for images and videos of the same size. They're best for images and the videos that have same size, the total number of frames. So all the image data, this convolutional neural networks are very well. I mean, they are performing very well. What they do basically is before going towards the ordinary neural network, they actually perform a lot of feature extraction tasks. And the feature extraction tasks are also learnable. What kind of features you are going to learn, that is that the model will decide rather than the human engineered features. So and then we have recurrent neural networks, RNNs, that are best for sequence data. For example, the data with different lengths in the inputs or different lengths in the outputs. For example, if you want to recognize activities in videos, then one video may have large number of frames, another video may have small number of frames and stuff like so. Although the activities, the total number of activities may be finite, that's a classification problem, but the input may vary. The input length may vary. Similarly, if you want to recognize speech recognition, for example, the audio signals, they may vary from the length, even the input size. They can vary. And if you want to convert, for example, speech to text, the outputs, they also vary. Some input audio signals, they generate text with larger length. Another audio signal may generate text with smaller length and stuff like so. So wherever you have sequence data, whether inputs or outputs, you will use the recurrent neural networks that are, all these convolutional neural networks or recurrent neural networks. There are others as well, generative adversarial neural networks and stuff like so. There are so many, but the basic building block comes from this basic neural network, and all the rest of the models are just the specializations of these. So next we discussed a general or common machine learning pipeline. What we have to do to come up with a machine learning project. What are the necessary steps, or what are the sequence of steps to accomplish this? The first and the foremost task is data collection. This is important. Data is very much important these days. So for example, one may think that data collection is easy task. In certain cases, yes, data normally is available, but in a lot of cases, data collection is really a tough task. People are spending a lot of budget on just data collection and labeling of the data, getting prepared the data for classification or regression or whatever model you want to fit in. So data collection, where you want to collect the data, what kind of data you want to collect, how to ensure the consistency, how to ensure the diversity, to get a sample that actually represent the population and stuff like so. Data collection is can be a tedious and can be an expensive task, or it can be a simple task. It completely depends what kind of application you're going to working on. After collection of the data, a significant amount of time actually is spent on data pre-processing, or sometimes called the data preparation. We may have to clean the data. There may be missing values. There may be values that are, for example, unscaled values, outliers, and all that kind of stuff. So several times, for example, we rescale the data. We may have outliers, for example, outliers in the data, missing values in the data. We may have text data that we need to convert to numerics using some encoding. And we may have to standardize data. We may have to apply some normalization on features. We may have to do some dimensionality reduction if we want to, or if it is required to. All that kind of stuff that appears in data pre-processing. And the output of this module is actually the prepared data or the ready data for machine learning model. Next, depending upon the problem at hand, we actually need to select the model, and that's the most tricky part. What model you are going to select for your problem? Even you know, for example, your problem is classification problem. Still, there are several classification models. Which one to pick? Um, if you're going to pick, for example, the most simple model in terms of the number of parameters, that may not be very well for your data. Or if you pick a very complicated or flexible model, that may not be very well, that may overfit or may have other issues. So whether you're going to select the model from the available models or you have to come up with a new model for your data, that all falls under this model selection method. It is recommended, however, that there are certain models that perform on most of the data sets that perform very well, and there are results for those. Heuristics or rules of thumb are to use basically those kind of models as a first try and see whether the performance is in a way acceptable for you or not, and then go further and tweak the result, tweak the model, and select further models or maybe tune its parameters and stuff like so. Rather than to go and building a model from scratch, you can go and build a model for your data from scratch, but this is not recommended. It may eat a lot of your time. So it is recommended to first use the available models and get the parameters tuned and see whether the results are up to your requirement or not and stuff like so. But this model selection is really a complete kind of a mess one may have to go through. Then we have model training. Once we have selected and finalized our model, the next part is how to train the model. We have already data, we have data available, we have model to train, we have availability of that. Next task is model training. We need to train the model. There are multiple training policies. How to train a model, there are multiple choices in there as well. What kind of optimization algorithm we are going to use, what kind of training procedure we are going to use, and particularly, for example, in deep learning or neural networks, there are a lot of ways to actually train, whether we are going towards whether we are going to apply a plain gradient descent algorithm or stochastic gradient descent or batch or mini batch, and what kind of acceleration and all that stuff. So sometimes even with the availability of data and finalization of the model training may have a lot of choices, and we may have to come up with the one that may be acceptable, and we may have to switch back and forth and check which one is the best for our data. After training, we might have at the training time, we might have reserved some data for evaluation, sometimes called the validation data, also called the development data or development set. Then after the training, we have to evaluate our model to get an expected generalization or the performance on unseen data. And if you're satisfied, we should just go and deploy. Incremental learning normally happens, for example, when more and more data appears, you need to adjust that data, and you need to utilize that data in training as well. So one form of incremental training is more data, you collect more data, you pre-process more data, and now you want to utilize that data to improve your model training as well. And the second form might be that you have deployed your model and you get certain feedbacks that on these particular examples the model is performing this much, and maybe the result should be other way around and stuff. So sometimes through feedbacks, and most of the time through more data, and on very few cases through feedbacks. Incremental training also run, which means you may have to retrain the model and evaluate, or in some cases you may have to select the model again and may have to go through the whole pipeline. It completely depends. So that's the general pipeline of machine learning project, any machine learning project. The steps can be further expanded or maybe compressed, for example, to explain for example, the model selection, model training, and model evaluation. These three can be combined in one, for example, one bigger abstract task. Similarly, data collection and preparation can be combined into one task, or just to explain the high level view, or maybe each of these tasks can be expanded further to explain each and every one in more detail. But that's how the general pipeline looks like.